Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Hope you and your family in the best of health. Lecture for grade 10, subject chemistry, chapter number 9, lecture number 3, and here is Mrs. Saira Jamal. Dear students, today I am going to talk about self-assessment exercise 9.2. Question number 1. Following reaction can occur during thunderstorms. 3 moles of oxygen molecules, they react together to form 2 moles of ozone molecules. O3 is the formula of ozone. How ozone is formed? Ozone is formed from the oxygen molecules. Oxygen molecules will react together to form ozone molecules. 3 moles of oxygen will give 2 moles of ozone. Derive the equilibrium constant expression for this reaction. If you remember in the previous lecture, I told you how to derive the equilibrium constant expression for a general reaction. Over there, we use a general reaction where we use A, B as a reactants and C, D as a product. But in this case, we have to find out the equilibrium constant expression for this reversible reaction. It means that by using the law of mass action, we can find out the equilibrium constant expression for any type of reversible reaction. Let us derive the equilibrium constant expression for this reversible reaction. We know that according to law of mass action, the rate of forward reaction is proportional to the active mass of the reactant. Active mass of the reactant substances or active mass of the reactant. Reactant in this case is ozone molecule, and active mass I told you is the concentration of oxygen molecule in moles per decimeter cube, which is also called molar concentration. To remove the proportionality sign, we will use rate constant for forward reaction Kf. For the reverse reaction, we will do the same. Rate of reverse reaction is proportional to the active mass of the product. Active mass of the product is ozone molecule. O3, ozone molecule raised to the power its coefficient in the balanced chemical equation. Coefficient of ozone is 2, or number of moles of ozone is 2. Number of moles of oxygen molecules are 3. That's why we use 3 as a power in this case and 2 as a power in this case. Now to remove the proportionality sign, we will use the rate constant Kf, rate constant for the reverse reaction Kr. Kr is the R shows the reversible reaction. O3 and active mass by using the square brackets with power 2. 2 again I told you is the coefficient. Where Kf and Kr are rate constants for forward and reverse reaction respectively, then at equilibrium state what happened? The rate of forward reaction becomes equal to the rate of reverse reaction. By putting the values of rate of forward reaction and rate of reverse reaction, rate of forward reaction value is Kf, oxygen, active mass of oxygen raised to the power its coefficient, and rate constant for the reversible reaction, active mass of the ozone raised to the power its coefficient in the balanced chemical equation. Now by keeping the constant at one side and the variables at the other side, Kf and Kr are the constants, and concentration of ozone and oxygen molecules are the variable. We will write them at one side and the constant at the other side. Now Kf over Kr, we know that it is Kf over Kr is equal to a single constant. Instead of using these two constants, we will use a single constant for the reversible reaction, that is called Kc. Kc is the rate constant for a reversible reaction. So this is the equilibrium constant expression for this reversible reaction for the formation of ozone molecule is this expression is for this reaction. So you can use this method and you can derive the equilibrium constant expression for any type of the reversible reaction. In this question, as they ask derive the equilibrium constant expression, so derive means we have to follow all the steps. In the second question, they only asked us to write the equilibrium constant expression. Only we have to write the equilibrium constant expression. We will not derive it, or there is no need to derive it, because in the question they ask only about writing the equilibrium constant expression. Question number 1 is 4 moles of hydrochloric acid react with 1 mole of oxygen and give 2 moles of water and 2 moles of chlorine gas. For this reversible reaction, you will write the Kc, or equilibrium constant expression. So Kc is equal to the product of the active masses of the product over the product of the active masses of the reactant raised to the power their coefficient in the balanced chemical equation. Coefficient of this reactant is 4, we will write 4 as a power. Coefficient of this reaction is 2, we will write 2 as a power. Coefficient of this reaction, chlorine, is 2, we will write 2 as a power. Oxygen is also here, I forgot to mention oxygen. Oxygen is also a reactant, so in a square bracket we will also write oxygen. Second equation is acetic acid when react with ethanol, it will give ethyl acetate and water. Ethyl acetate and water are the product. So we will write the products in numerator, active masses of the product in numerator, and active masses of the reactants in denominator. So we will write the reactants in denominator and both the products in numerator with square bracket. Square bracket, again I told you, shows the active mass, or active mass means their concentration in mole per decimeter cube. Third example is hydrofluoric acid. 2 moles of hydrofluoric acid will decompose and will form 1 mole of hydrogen gas and 1 mole of the chlorine gas. Kc expression, again we will write the active masses of the product in numerator and active mass of the reactant in denominator raised to the power its coefficient is 2, and the coefficient of hydrogen and chlorine is 1 1, or their number of moles are 1 1, so no need to mention 1 1 on as a power. Fourth example is 2 moles of nitrogen dioxide will give us 1 mole of nitrogen tetraoxide. So nitrogen tetraoxide is the product. We will write the active mass of the product in numerator and the active masses of the reactants in denominator. So denominator and the power of 2 is the number of moles of nitrogen dioxide, or in other words, the coefficient appear in this balanced chemical equation. Example 9.2. Example 9.2 is coal can be converted to a gaseous fuel as methane. Methane, you know, is the main component of the natural gas, and methane can also be formed from coal. Coal reacts with hot steam to form carbon monoxide and hydrogen, and then these gases can react further to give methane. It means methane production takes place in 2 steps. The first step is first coal react with hot water or with steam to form carbon monoxide and hydrogen gas. In the second step, this carbon monoxide and hydrogen gas then react will form methane and water. So this is the final step, or the step where the production of methane will take place. For this step, for the final step, or for the second step, we have to write, not derive. We have just write equilibrium constant expression for this reaction. So Kc equal to, as I told you, that the product we will write it in the numerator and reactants in the denominator, and we will write them in square brackets, and then the power each concentration, raise each concentration to the power that corresponds to the coefficient of each species in the balanced chemical equation. The powers are actually their coefficient or their number of moles in the balanced chemical equation. Now let us write the Kc expression. Kc is equal to active mass of the products. Two products are there, methane and water. Methane and water, as their coefficient is 1 1, or there is nothing means 1 1, 1 mole methane and 1 mole water. So no need to mention 1 1 here. And the concentration of the or the reactant we write in the denominator, raised to the power. The coefficient of hydrogen is 3, so we will write 3 as a power. Next topic is conditions for equilibrium. It means that a reaction will be in equilibrium state, or a reaction will attain an equilibrium state only if it will fulfill the following conditions. The first condition to fulfill is the an equilibrium is achievable only in closed container or system in which substances neither leave or enter. Equilibrium will establish only in that case when the container or the system are closed. You can see here we have a flask and there is a cap or a lid on that flask. That cap or lid will make this flask a closed system. The gases cannot move out, and another gases or any other thing cannot move inside. So this type of system in which a substance can neither enter or neither leave is called a closed system. So the first condition to achieve equilibrium is the system must be a closed system, or the container must be a closed container. Second, at equilibrium, the reaction does not stop. Forward and reverse reactions keep on taking place at the same rate but in opposite direction. You can see hydrogen gas and iodine gas, they will combine together to form hydrogen iodide gas. So the purple color fades, and in the forward direction, the purple color of iodine fades or it becomes lighter. But in the reverse reaction, when hydrogen iodide gas again decompose, this is called decomposition or breakdown. It breaks into iodine gas and hydrogen gas, so the purple color of iodine will reappear. So you can see this conversion of iodine color into fat color or into light color is combination of hydrogen and iodine to form hydrogen iodide, and the reverse reaction is hydrogen iodide gas will decompose or breaks down and will give iodine gas and hydrogen gas back. So forward and reverse reaction will take place at the same rate, but they are in the opposite direction. Forward reaction move from left to right, and reverse reaction move from right to left. Third condition is an equilibrium state is attainable from either way, that is starting from reactants or from product side. If we will see or we will consider the product at the start, what will happen? The product will convert it into the reactant and again reactant into product, and this process will continue until the rate of reaction of forward and reverse reaction become equal and equilibrium will establish. So no matter the reaction start from this side or it started from this side, equilibrium will establish. Fourth condition, at equilibrium state, the amount, concentration of reactant and products do not change. Don't change the amount of hydrogen gas or amount of iodine gas or hydrogen iodide gas. Don't change their amount. If you will not change their concentration or their amount, the reaction will remain in equilibrium state for a long time. Same if you will keep temperature unchanged, if you will keep pressure or volume of the system unchanged, what will happen by keeping this condition same, the equilibrium will establish for a long time, or the reaction will be in equilibrium state for long time. Seventh condition is if an equilibrium state can be disturbed. How can we disturb an equilibrium state? We can disturb an equilibrium state by changing concentration, temperature, or pressure or volume of a system. And suppose if you change the condition or if we disturb the reaction, so what will happen? A new equilibrium can be established, or a new equilibrium can be attained by keeping the condition constant. Don't change the condition more. Once if you change the condition, then the equilibrium will disturb and a new equilibrium will form. Now don't change the condition. If you will not change the condition this time, the reaction will be in equilibrium state for long time. Ways to recognize equilibrium. How can you identify the equilibrium state? Like how can you recognize the equilibrium state? Like you will come to know that the reaction is now in equilibrium state, and this is the standard state, or you can say the dynamic equilibrium state. There are two important ways by which we can recognize the equilibrium state. First one is physical method. Example of physical method is spectroscopy. It means by spectroscopic technique, we can identify or we can recognize the equilibrium state. But this spectroscopy, inshallah, you will learn in detail in grade first year. Second is chemical method. Example of chemical method is titration. What is titration? It is a technique where a solution of known concentration is used to determine the concentration of an unknown solution. Concentration of known solution means suppose one of the solution is HCl, and we know that the concentration of HCl is 0.1 molar or 0.2 molar or 0.5 molar. If we know its concentration, it means that this is a solution of known concentration. And if we have one more solution, like suppose sodium hydroxide, and we don't know about the concentration of sodium hydroxide, so we will call it a solution of unknown concentration. Here the concentration of reactants and products at regular intervals are determined. When we start the practical, we will take concentration of reactant and product at regular time interval, and then we will find out the individual concentration of each reactant and each product. We will continue the process until we observe the constant value. When the concentration of reactant and product become constant, that point is called the equilibrium state. Equilibrium constant and its units. What is equilibrium constant? Equilibrium constant is defined as a ratio of the product of concentration of products to the product of concentration of reactants, each raised to the power equal to the coefficient in a balanced chemical equation. Although I told you in detail about the equilibrium constant, over here I'm again telling you about the Kc. How can we write it in this form as well? Equilibrium constant Kc is equal to product of concentration of products raised to the power of coefficients, and over product of concentration of reactants raised to the power of coefficients. It is conventional to write the product side in numerator and reactants as in denominator. So reactant each raised to the power the numerator and reactant as denominator. By knowing the balanced chemical equation for a reversible reaction, we can write the equilibrium expression. Thus we can calculate the numerical value of Kc. Numerical value of Kc means we can find out the unit of Kc. Now, there are two important things which we have to keep in your mind. The first thing is that the Kc has no units. The Kc has no units in reaction where the number of moles of reactants are equal to the number of moles of the product. When the number of moles of reactant and products are equal, like in this example, you can see 1 mole of hydrogen react with 1 mole of iodine and will give 2 moles of hydrogen iodide. How many moles are at the reactant side? 1 plus 1, 2 moles. How many moles are at the product side? 2 moles. So 2 moles reactant will give 2 moles of product. In this reaction, the number of moles of reactant and product are same. So the Kc has no unit. And the second case is, or in this case, why the Kc has no unit? This is because the concentration units cancel out in expression for Kc. We will do example in the next slide. Those reversible reactions in which the total number of moles of reactants are different from total number of moles of products in a balanced chemical equation. If the number of moles of reactants are different from the number of moles of products in a chemical equation, then in that case, Kc has units. For example, nitrogen tetraoxide will decompose to give nitrogen dioxide, 2 moles of nitrogen dioxide. How many moles are at the reactant side? Only 1 mole. How many moles are at the product side? 2 moles. It means the number of moles of reactant and products are different. So in this case, Kc has unit. Example 9.3, determine the unit of equilibrium constant for the following reaction. There are some reactions, and for those reactions we have to find out the unit of Kc. The first example is hydrogen will react with iodine to form hydrogen iodide. What is the first step? The first step is write the Kc expression for this reaction. You will first write the Kc expression for this reaction. You will write the active mass of product in numerator with the exponent with the coefficient as a power, and the active masses of the reactant in denominator. This is the first step. How to find out the unit of Kc is, first we will write the product, active mass of product in numerator along with its coefficient as a power, and then the active masses of the reactant in denominator. Now we will write their unit. This I told you that the square bracket or the active mass means the concentration of reactant and products in moles per decimeter cube, and as here the power is 2, we will also use the power 2. Now we will write the mole or the molar concentration of hydrogen in iodine also. This is the molar concentration of for hydrogen and molar concentration for iodine. Mole per decimeter cube for hydrogen and mole per decimeter cube for iodine. And in numerator we have 2 moles per decimeter. These 2 moles per decimeter cube will cancel out with the 2 moles of per decimeter cube in the denominator. As a result, Kc will has no unit. In this case, the number of moles of reactant are equal to the number of moles of product. Hence, the Kc has no units. Second example is for nitrogen tetraoxide. Nitrogen tetraoxide, when decomposed, will give 2 moles of nitrogen dioxide. This is again another reversible reaction. The first step I told you, we will write the Kc expression for this reaction. We will write the product in numerator and the coefficient as a power, and the reactant in denominator. Now we will put their units. Unit for the first case of for the product is mole per decimeter cube with power 2, and for the reactant is mole per decimeter cube with power 1. No need to mention 1. So 2, here we have 1 and 1. These concentration will cancel out, but still mole per decimeter cube is left. This mole per decimeter cube which is left in numerator is the unit of Kc for this reaction, for nitrogen tetraoxide decomposition constant. Another example is nitric oxide. When react with oxygen, it will give nitrogen dioxide. 2 moles of nitric oxide will react with oxygen and will form 2 moles of nitrogen dioxide. The first thing, as I told you before, we will write the Kc expression. For Kc expression, we will write the product in numerator and the coefficient of product as a power, and the reactants in denominator. Again, the coefficient will go in power. So this 2 will be write as a power. Now we will put the units. Unit for this nitrogen dioxide, mole per decimeter cube with power 2, and mole per decimeter cube for nitric oxide with power 2, and mole per decimeter cube with no power. So this 2 will cancel out with this 2. Still 1 over mole per decimeter cube is left. 1, because all the values cancel out and in the numerator, and in the denominator mole per decimeter cube is left. When we will take this mole per decimeter cube up, you can see mole positive 1 will convert it into mole positive negative 1 mole per mole, and then negative decimeter cube will convert it into positive decimeter cube. Positive will become negative and negative will become positive. So per mole decimeter cube will be the unit for this reaction. Then self-assessment exercise 9.3. It is your homework because it is related with the same topic. You have to find out the unit for the some reactions. Importance of equilibrium constant. Why we use equilibrium constant? What is the importance of equilibrium constant? This Kc. The first importance or the in order to find out the importance of Kc, knowing the numerical value of equilibrium constant Kc. Numerical value means if you will put numbers or values in the Kc formula or in the Kc expression, those values will give us many information about the chemical reaction. Many important features we can predict it or we can find out by using those numerical values. What are those features which we can predict by using the numerical values or the number values of the Kc? The first importance or application of equilibrium constant is by using the equilibrium constant Kc, we can determine the concentration of reaction mixture at equilibrium state, or determine the equilibrium concentration of equilibrium mixture by knowing the initial concentration of reactant. If we know the initial concentration of a mixture, then we will be able to find out the concentration of the other reactants and the products as well, because you know that the equilibrium mixture I told you before contain all the reactants and all the products in it. So if we know the concentration of reactants, we can find out the concentration of the products as well. If we know the initial concentration of reactant and if we know the equilibrium constant Kc value, then we can find out the concentration of the product. Equilibrium mixture is a mixture in which components of both reactants and products are present. Reactants and products all will be present. You can see hydrogen and iodine are the reactant and they will react together to form hydrogen iodide as a product. In reaction mixture, hydrogen gas, iodine gas, and hydrogen iodide all will be present. So if we know the concentration of these two reactant, hydrogen and iodine, and also we know the Kc value, then it will be easy for us to find out the concentration of this product or hydrogen iodide. Second important feature which we can predict or we can find out by using the Kc expression is, or the Kc value is, predict the direction of a chemical reaction. We can predict, we can find out that either a reaction is going in forward direction or it is moving in the reverse direction. We will take some amount of reaction mixture at any time and will find the concentration of reaction mixture, means reactants and products, after a regular interval of time. And then by putting these values in the equilibrium constant expression, we will find a value, but that value we will call it QC, not KC, because KC is only the values at equilibrium state. But if we will take the concentration of the equilibrium mixture, and then we will find out its constant value, that will be called quotient QC. That value will be called quotient QC. For example, if you know the concentration of hydrogen iodide, that is 0.40 and 2 is the power, and the concentration of hydrogen is 0.10 and that of iodine is 0.20. By solving it, we will get the answer 8. As Kc or Qc has no units, we will just write 8. Now compare the value, this value QC with the Kc. Kc means the value at 57. The value of Kc is 57 at 700 Kelvin temperature. And the value at any point, not at equilibrium point, is QC, which is 8. So you can see 8 is very, very smaller value than 57. So if the value of QC is very smaller than KC, value of QC is very smaller than KC, it means that reaction is not in equilibrium. It requires more product to be formed. Therefore, reaction will move in forward direction to form more product. But if the QC value is very greater than KC, it means that the reaction will move in the reverse direction, and if the value of QC is equal to KC, it means equilibrium has been attained. So from the value of QC, we can identify the direction of a reaction, that either the reaction is moving in forward direction or moving in the reverse direction, or the rate of forward and reverse direction is same and equilibrium is attained. Then the third importance of equilibrium constant expression is, the equilibrium constant is, predict the extent of a chemical reaction. Extent means quantity, how much quantity of product has formed in equilibrium state. More product is formed or less product is formed, or no more, nor less products are formed. So very large value of Kc indicates that more product has formed and reaction has almost gone to completion, because if all the reactants are converted into product, it means the reaction has almost gone to completion. And very small value of Kc at equilibrium means that the little product has formed and the reaction never goes to completion, because still most of the reactant is left unreacted and it will react and then will form product. Neither small nor large values means comparable amount of reactants and products are present at equilibrium. It means reactants and product, their concentration is almost same. The fourth importance of the equilibrium constant is that predict the effect of change in conditions. What are those conditions? Concentration. If we will change concentration of any of the reactant or product, what will happen to the reaction? If we will change temperature, pressure of the chemical reaction, then what will happen and what will be the effect on the equilibrium?